All right, we're going to go ahead and get started with this next session, which is interesting in that we're actually looking at sludge and the possible opportunities. So I'd like to introduce Dr. John Dietz. John has over 33 years of multidiscipline consulting experience, including the past 18 as an environmental engineer. He has experience in active and passive mine drainage treatment, research and development of new innovative anaerobic vertical flow wetlands, the Clean Water Act, National Pollution Discharge Elimination System, NPDES studies, Clean Water Act, Chapter 404 wetland protection and mitigation, and environmental and ecological assessments. So I'd like to introduce Dr. John Dietz.
Thank you, Jane. Today's presentation is going to be kind of parallel to one that was yesterday with this vehicle related to sludge application. The sludge actually comes in this treatment system. So what we're going to be talking about is the Orchid Smale active treatment system that was installed. We're approaching 8 years ago now, and how that system works and how it's remotely monitored to make sure that the system is working continuously. So this discharge is located in the Mill Creek watershed in Clarion and Johnson County. It's one of many discharges that it says here is on forfeiture site. Unlike most of the discharges that I've worked on in this watershed and go past the treatment system or are actually related to abandoned mines. So this is kind of a unique, different project in that it was on forfeiture site related to an active mine. So first, I'd like to talk about the failed passive system and the conditions that were there. The Orchid Smale passive system, there were two passive systems called north and south. There was the designs were done by NRCS, with the systems from Demarest. It was a state-of-the-art system at the time. And I'm going to go through a few things. There's nothing wrong overall with the approach at the time. As we all know in passive treatment technologies, we learned more and more as we went along. We found out what worked and what kind of discharges and what didn't work. And this was a system that was nothing flawed in the design overall. It's just that it was a system that was built at a time where there was limited knowledge on chemistry and the overall effectiveness of passive.
Excuse me, John. Can we move the microphone up a little bit? Yeah. There we go.
Sorry about that. And so it was constructed in 2006 at a cost of approximately $1.1 million. Initially, it worked very well. We required a lot of operation and great flushing components. However, after several years of operation, there was signs of deterioration, some of which I'll go through. Finally, the effluent deteriorated to the point that it became acidic and started discharging considerable amount of metals, including iron and manganese. And eventually there were overall failures, which you'll see in the following picture. So what was the cause of the failure? You can look at So we can look at the chemistry of the two discharges, the north and the south. A couple of things will become quite clear, which is high acidities, 600, 250, cold acidities, also very high. Cold acidities related to the carbon dioxide in the water. It's important in active design for the amount of iron that you're using. But when we really start focusing on the iron concentrations, we see very high iron concentrations of over 150 and 300. Manganese concentrations, this is some of the highest manganese concentrations I've seen. This is discharge is over 100 milligrams per liter. Aluminums are high in the north discharge, but also in the south discharge. So when we look at the relationship to a risk table developed by DEP, AMR, And again, this risk table was developed after the passive treatment system was designed and installed. So there's, again, no criticism here at all. It's just that what we've learned in the overall process is that the sum of the iron and aluminum concentrations greater than 50 milligrams per liter places you in an extremely high risk for failure. So based on the chemistry that we now know, or at least that we learned from the passive treatment systems, this was a high peak or high risk discharges where we probably wouldn't even consider passive treatment currently. So this was what the passive system looked like aerially. This was the south. There was the ALD on the drain pond, SAPs, and then another settling pond. The north discharge ended here, went into the initial settling pond and SAPs. These were flushing ponds as well as settling ponds. We're using multiple SAPs. And then this was also a SAPs, but as you can see, iron concentrations became very orange in coloration. And future slides, couple slides following will show what happens in those. So problems with it, with the iron concentration accumulation, there were channel breaches. There was limited iron removal due to accumulation of metals and decreased tension time, and also the low pH, which also reduced the overall oxidation and precipitation of the iron. And then what we also saw was embankment and channel breaches, where water would be flowing over the embankments as a result of lower permeability in the SAP, resulting in erosion of the embankments short the passive system. These give you an idea of what I'm talking about here. This is the weir that was installed. You can see how much iron concentration, iron accumulation is occurring over the weir. That ended up clogging the channel, high maintenance issue related to, this was filling up and breaching in that months, not years, 2 years. And then we'd also start seeing these kind of conditions where due to channel filling in, sediment build up in the SAP as the embankments would overcome. One of the other things that we also did see with respect to the SAP is that there would be reduced permeability, which caused an overflow. By the criticism of the design, there were no emergency spillways in this system. So as a result, overtopping was what was going to happen. We had reduced permeability in the SAPs, and that's what you see here and that here. So flows began to decrease through the SAPs as well. Effects of flushing. This is how much metal accumulation you can see in the SAP, but because of repeated and recurring flushing, there would be these drains that would occur that would go directly through the compost layer into the limestone layer, eventually clogging the limestone layer, reducing permeability. So in 2014, as I mentioned, the system's been operating for about 8 years. Competitive bid went out between the DEP and Headwater Carroll Trust managing it, and for design of design of the new system. We proposed an active system using a line slurry and reactor system. Now we get into the various components. It shows here, startup was 2014. So, this gives you the size of the existing passive treatment system that we utilized and revitalized, and this is the footprint of the active treatment system in that small area. So it really is only one settling pond. This is actually with the whole system operating. So you can see that we collect the water, bring it into the active system, settling basin, polishing pond, and then we just let it flow through the rest of the passive system. The north, the south components, those were converted to flood channel. And yesterday's presentation talked about that sled in this application. So effluent quality that has been perpetual since 2014. Constructed effluent quality acidity has been always less than alkalinity. So it's a net alkaline discharge, iron concentration for less than 1. Total aluminum is less than 0.3, and that's been on a continuous basis since the went into operation. Manganese will vary, but that varies based on how the plant is operated by DEP and a function of PA, which I have a slide and briefly talk about. So, with respect to the active treatment system, you're looking at the whole thing right here. This is a lime slurry tank. 35% lime slurry is brought on site, pumped into the tank, continuously mixed in that tank. And here is the control system as well as the lime slurry pumps. So the lime slurry is pumped through pumps and is fed into the reactor system at that point. And these are just duplex blowers to provide the aeration for key components of the reactor. And that reactor sits right here. More details on the reactor. Again, I mentioned the duplex blower. One of the things we did is we had aeration is pretty critical to this treatment process. So we had an operating to backup. And it also allowed a pretty unique situation where all maintenance to be done on mixers and the various components once a year, because these are duplex and normally require maintenance every 6 months. But they're duplex. With respect to the reactor system, there are 2 zones in it. Water comes in here. There's what we call a pre-aeration zone. That pre-aeration zone is designed to drive off carbon dioxide. That reduces lime use for more effective use. And it's as a result, it also limits the amount of scaling that may occur in the system as well due to calcium. As I mentioned, the lime slurry is pumped into this point, then flows into a reactor system with 2 mixers and also aeration in here, where the air is mixed and aerated to oxidize the iron into an insoluble form of ferrous with ferrous.
Hey, John, can you speak up a little bit?
Yep.
Oh, isn't it? There you go.
There we go. This shows the lime slurry pumps. They're very simple hose pumps, very effective, low maintenance. They're VFD controlled, and we set the flow rate based on a target pH. The system was designed to be pH controlled. However, because of the low variability in flow and chemistry, the changes are gradual, so the operator determined it was better to just use pH as a monitor and just adjust the lime slurry feed rate to that target pH maintenance. So this is where we really, this is the focus of it. How do we make an active system be able to be monitored remotely so that we know that it's working without having an operator there on a daily basis? One of the things I should mention as far as the active treatment operation of this plant, the operator visits the plant twice a week for 2 hours. So we have a full 4-hour time for operation of the system. Now the maintenance part of it, which has to deal with sludge handling and equipment, is separate from that. Just the routine operation, pH control, and system operations 4 hours. So within the control system, this is all the electronics there are for various equipment, including the mixers, the blowers, and the lime slurry pumps. I would say this is the brains of the remote and is the remote monitoring unit. It's a little hard to see, but in the next slide, you'll see what it is. It's called an on-the-site crystal ball. This is something that was adapted from wastewater and water for pump stations. So it has various inputs that you can put into the unit for monitoring. And as in the case here, we have digital inputs that are on and off. In other words, we know whether something is functioning or it's not functioning, and put it into an alarm state if it's not working. And I'll show you some output, monitoring output that tells us whether or not we have a problem, how we set this up in alarm. At this site, we're not using the pump monitoring components, but say if you have a discharge that's pumping into your treatment system, you can tie in the pump monitoring components, and they're pretty flexible to use anything for pumps working or not, long term, whether your pump is deteriorating, whether it's maintenance. So pretty good component, but orchid smell, we didn't eat it. And then there's these analog data inputs, which I'll show you. Those allow us to put in 420 million signals so that we can track various lime slurry levels, pH. And I have actually one site where we're also monitoring turbidity. We have a clarifier, we put in the clarifier, if the clarifier is working, we'll be able to monitor it through turbidity. The other key component of this on-the-site unit is the alarm system. So it's a cellular internet-based system. It will phone call you with alarms, it text you with alarms, and you can set that up in the software that comes with it, which is called Guard Dog Remote Monitoring.
Nice.
This would be the setup menu for the whole unit. So gives you an idea of what you can do with it. You have call out lists, you have manage call out plans. That'll tell you what you set your alarms at so that it will alarm you if the pH drops, it will alarm you if your blower fails, it will alarm you if a mixer fails or the line slurry. Other things that you can do, device setup, you know, that these are things that you go into and you identify your device, you set your limits on your device, and then be able to set up your alarm outputs to the various people that you want to talk to, and how it's be administered for each individual through phone, text, or email. This is pretty good. Apologize for the size of it, but this kind of shows on the internet, you know, in other words, the web page for Guard Dog, what the system would look like. Green is good, red is bad. That may be an alarm, or it may be just, like I said, a duplex blower. So if the duplex blower is off, it will show red off. And down here are your analogs. Yeah, I can't all that. So it will record pH, pH, line slurry level, whether your line slurry pump is working and what rate. So this is a little more visible. That was just to give you an idea of how you go to set up online with it. This shows what it looks like on your cell phone. So, you know, I have two systems of monitoring currently as far as the operation of the system, and hopefully it'll get off of it. I'll get off the alarm list so I don't get woken up. But soon the operator will take on. But what you can see here is that you have two blowers. In this case, we're looking at smell. Blower 1 is operating, blower 2 is off, and that's the duplex component. If we checked it 12 hours later, we would see the exact opposite. The blower 1 would be on, blower 2 would be off. Aeration mixers, line slurry mixers, pump hoses. So in other words, in these pumps, there's a sensor in them that says the pump, if the hose breaks, we have water level indication inside the hose pump that will trigger an alarm that calls that we have break. And then we also have over here backup battery, primary power. So in other words, if you lose power in the site, this is how you that we can smell what we have there is we have a hookup for a generator. So if we lose power, the operator has about 4 or 5 hours to bring this generator out. We have one on the site. Plug it in, turn it on, and it's other components, like I said, pH tells us what the pH is fine. If we set our bandwidth, the range for that pH, in other words, in this situation, the pH drop below 8.5 it would send the alarm. So that shows that the pH is good. They're currently operating, you know, that time we were operating at 9.3. And we can see that online. You can see what the line slurry level is. This is also a unique one in that one of the other people or companies that can monitor is chemical supply company. So if you were using sodium hydroxide, in this case we're using line slurry, that's being reported to chemical companies. So nobody has to call them to order. They see what the level is. We'll just automatically bring it delivery. And then finally, your pump speed. this tells us what speed we're at, 5.25 hertz out of 60 hertz, so the pump is running. Pump 2, this is just a little glitch in 40-20 milliamp signals, so it never gets quite to 0. But that red tells us that it's off, but it's in a backup state. So if pump 1 failed, the operator can come out, turn off pump 2 as a backup. So you know, we look at the critical components and what we need as far as backup. Now, with respect to the analogs, this is the other thing you can get out of this, and this can actually be charted so that we can look long term how the pH is changing over time, and how the lime slurry levels are changing over time, so that we can see if we're having electrode problems, calibration, with respect to the lime slurry levels, we can look at utilization rates, and as I said, plan and predict when we do delivery. And then the sled pump is just, you know, telling us that it's working and at what speed that the operator places it at. So if you're the operator, this is a useful tool for you. To, you know, it's going to set alarms and you can monitor the system while you're away in a matter of minutes. And as the overall manager, say if you're in this case, they have access to this too, so they can see how the operator is actually operating. And finally, I mentioned with respect to the effluent quality and operating conditions, mostly the manganese removal, as you can see, is a function of pH. Total manganese at pH 9 is around 9 milligrams per liter, drops to about 6 milligrams per liter at 9.7, and to get to less than 1 milligram per liter, you got to push the pH up over. So it is completely a pH dependent relationship. I will mention in our original proposal, we actually had a hybrid system design where we were going to use the pH neutralization to remove the aluminum and the iron concentration, and basically scalp a large percentage of the manganese. I think I'll mention that the raw water chemistry for manganese was 70 or 80 milligrams per liter. So in other words, even at pH 9.1, we removed about 90%. And that ends up making this water healthy. And that's satisfactory for restoration. But say if you were regulatory, the network limits, it's a mining company, that's not going to get you there. You would have to operate at a much higher pH and a much higher line utilization than federal scales. But in this case, what the plan was to build a hybrid system where we would use limestone beds for manganese removal, but we would use most of the manganese at a pH of 9 and basically move 9% that way and make it passive. And with that, I get to the last slide, and it raises the question, you know, we can remotely monitor active systems this way, and on a continuous basis as possible. You know, the one nice thing about passive systems, we can build them. We can go out and check them as long as the flows are going through, check the chemistry. We know 3 weeks, 4 weeks later, we're going to have roughly the same chemistry. With this active system component and remote monitoring, is it possible that you can achieve the same goals for chemistries that you just can't treat using passive treatment systems? So it does raise a possibility that small active treatment systems that you would very likely can use active treatment systems versus passive for discharges that you normally would not get to treat with passive and achieve water quality goals and watershed restoration. And I will mention with respect to Mill Creek in this active treatment system, this flows into a tributary of Mill Creek called Little Mill Creek. And since this was installed, Mill Creek has maintained the wild trout fishery. So in the long term, it has worked. It has been a component in the overall restoration of Little Mill Creek. With that, I'll take questions.
Any questions for John?
Grab that mic and turn it on. For the crowd, though.
I have a, let's see, I don't know what it's like here. But we're looking at roughly 10 to 15 hours old. So we're under $20,000.
Yeah, Jim's question was, asking about the electric cost in case you didn't hear his question.
Yeah, for the group that is listening online, what is the electrical cost associated with this plan? So it is an interesting question. You know, when we look at the overall cost of the active treatment system, you know, as I mentioned, the passive treatment system was $1.1 million. This entire active treatment system and revitalization clean out of the passive system is under $70,000. So it does raise the question, can active treatment from a cost basis you replace that? And if you're able to build an active system from the get-go without a lot of the ancillary working, this might be possible for $600,000. That leaves another $500,000 for long-term operation. And then putting it into the trust, it'll probably get you pretty close.
What was that dollar amount
And
again?
that was
For the active system?
Yeah.
Dollar amount for the active system was it was between $600,000 and $700,000.
it was 650,000.
Okay.
Janie would know. because
Okay.
She managed. She managed
I was the money.
Yeah, she was the money.
Okay. They're just
Now,
asking
for
online.
the monitoring there, is your internet based off cellular, or do you have to have internet to the site to monitor?
It's completely a cellular system, so the information from the on-the-site crystal ball is sent out cellularly, and then it's fed into it's an app for your smartphone or into their internet-based website, so you can monitor and set up either on the internet or receive the information cellularly.
Which sure you're on. For people online.
Oh. What is your annual total operation cost, chemical, electric, and maintenance?
I haven't, you know, I haven't been cognizant of what the spending at the site. Our original estimates were a little over $100,000 per year, and that included all of the operation costs: the electricity, the line slurry, labor, and equipment maintenance. So I believe our total in 2008 was 70 to 75,000. So escalating it up through the course of the year, we're now over.
I have a question from online. This is George Watzlaff is asking, how is the sludge handled? What is the final disposal plan? And are you concerned about resolubilization of manganese?
The sludge handling is a process where the sludge, the solids are settled in settling ponds, and then the sludge is either pumped to a drying bed or in the geotubes. From that point, it dries over a period of time, or the waters over a period of time, never completely dry. And then DEP is working with the Game Commission on land application on game lands for food plot. And it because of the alkaline nature of the sludge, it seems to work really well. I think, you know, Chris Yeagel's presentation, he indicated there were some initial problems, but that was more related to over application. In other words, they actually raised the pH of the soils too high. And it just took time for the vegetation to reestablish. With respect to manganese, we're in a pretty oxidized form for manganese. If you go out and look at the dried material in the sludge, we don't see any resolubilization because it converts to a manganese hydroxide precipitate, and given enough time, will go to a pyrophosphate, like a black solid.
Any other questions? All right, thank you, John.
Thank you.